Hello dear friends, welcome my channels. Today's discussions is homotopy and general topology. So friends, I just read the total definitions. At first my target to read total definitions, and after that I shall try to explain everything. At first I need to discuss all the definitions, because definitions is very important for a learner. So homotopy: if and f dash are continuous map of the space x into space y, then f is homotopic to f dash. If there is a continuous map f such that x cross 0 to 1 tends to y, such that fx0 is equal to fx and fx1 equals to fx. For each x belongs to x, the map f is called homotopy between f and f dash. Path homotopic. So friends, what is f and f dash? If f dash are continuous map, this is the must included, that it should be continuous map, and the space x into space y, and the f is homotopic to f dash. When it is f dash, if there is a continuous map, suppose fx0 cross 0 comma 1 tends to y, such that fx comma 0 equals to fx and fx comma 1 equals to fx. For each x belongs to x, the map f is called homotopy between f and f dash. Path homotopic: two paths f and f dash, mapping the interval 0 comma 1 into x are said to be path homotopic f p f dash, and if they have the same initial x0 and same final path x1, if there is continuous map f such that 0 comma 1 cross 0 comma 1 to x, such that fs0 is equal to fs or fs1 equals to fs. So capital F, small f is 0, fs comma 0 is equal to fx, and capital A, f s comma 1 is equal to small fs. Capital F 0 comma t is equal to x0, and capital F 1 comma t equals to x1. For each s belongs to I and each t belongs to 0 comma I, the map f is called path homotopy between f and f dash. Straight line homotopy. So the map f is capital F is called path homotopy between f and f dash when fs comma 0 is equal to small fs and capital s comma 1 is equal to small fs. Capital F 0 comma t is equal to x0. Capital F 1 comma t equals to x1. Straight line homotopy: if f comma g such that x tends to r square, such that the map fx comma t is equal to 1 minus t fx plus t gx. fx comma t is equal to 1 minus t fx plus t gx is a homotopy between f and g, then f is called straight line homotopy. Contractible definitions. So friends, I just discussed definition. A space is contractible if the identity map Ix such that x tends to x is homotopic, a constant map a constant map. So a space is contractible if the homotopic map Ix such that x tends to x is homotopic, a constant map. Composition: if f is a path in x from x0 to x1 and g is path in x from x1 to x2, then composition f star to g of f and g is path h given by hs equal to f2s if s belongs to 0 comma half and g 2s minus 1 if s belongs to half comma 1. Simply connected: in simply connected space x, any two paths having the same initial final points are path homotopic. Homeomorphism induced by h: let h such that x comma x0 tends to y such that y0 be continuous map, and map h such that pi 1 x comma x0 and pi 1 y comma y0 is such that h star fluid f equals to h composed f. The map h star is called homeomorphism induced by h relative to the base point x0. Zero homeomorphisms: let A belongs to a subset of R to the power n and h such that A comma A0 tends to y comma y0 if h is extendable to a continuous map of R to the power n into y, then h star is zero homeomorphism. Fundamental group of first homotopy group: let X be a topological space. Let x0 belongs to x. The path in x that begins and ends at x0 is called loop based at x0 with the operation star is called fundamental group. This is the product 1 x comma x0 of x relative to the base point x0. Important theorems of fundamental group: if x is path connected and x0 comma x1 belongs to x, then pi 1 x1 x0 is isomorphic to pi 1 x comma x1. This is the number 1. Number 2, if a simply connected space x any two paths having the same initial final points are path homotopic. If h such that x0 x comma x0 x tends to comma x1 is identity map homeomorphism. If h such that x comma x0 y comma y0 is homeomorphism of x with y, then h is an isomorphism of pi 1 x comma x0 with pi 1 y comma y0. And if I such that x comma x0 tends to x comma x0 is identity map, then I is identity homeomorphism. So friends, I just discussed the definition. What is homotopy? Homotopy f such that x cross 0 comma 1 tends to y, where fx comma 0 equals to fx and fx comma 1 equals to fx. Just discuss the definition of homotopy. This definition of homotopy: contractible, simply connected, contractible composition, simply connected, and homeomorphism induced by h, zero homeomorphism, fundamental group. An important theorem on fundamental groups. Just small discussions, friends. Just small definition. I discuss only the definitions. Now I want to discuss homotopy. So friends, it is concept of topology which tells you when two maps between a pair of spaces can be continuously deformed from one to other. And let me define two continuous map. You will see that my definitions, homotopy definitions. This is the first definitions of my homotopy. F and F dash. Okay. So to the continuous map, I want to define that how can F and F dash. So I take F and G. F and G such that X tends to Y and X comma T implies F X comma capital F X comma T and F X comma 0 is equal to F X for all X belongs to capital X, and F X comma 1 equals to Gx. F X1 comma 1 is. Similarly, this problem is same, that you see that F dash X, F X comma 1 equals to F dash X and F X comma 0 is equal to F X. Because the map is F comma F dash such that X tends to Y. Now if you think T equals to time and 0 to T less than 1. If you think of T as a time parameter varying on the interval 0 to 1. So F equals to capital F equals to essentially the collection Ft such that X tends to Y, T belongs to 0, 1 and Ft X Xt, then F0 equals to F and F1 equals to G. The family of maps started with at time t equals to 0. It is equal to the map small time t equals to 1 map G. When t equals to 1, then map G tends to G map G, and when t equals to 0, then map F. And t equals to 0 becomes map F. Then in between every other map, Ft is also a continuous map. The way the Ft varies with respect to t is also continuous. That a whole part of saying that capital F is continuous. In some sense, what it means is that the map F in time is being deformed into the map G, means F is homotopic of G, like this kind of that F capital F, the map capital F is called homotopy between F and F dash. The map capital F is called homotopy between F and F dash. So that in here you can say it is the G, or you can write also F dash, no problem. So the map F in terms is being deformed into the map G as time varies. One can check that This is an equivalence relations. Reflexive, one can check that this is symmetric equivalence relations. This relations is equivalence, reflexive, symmetric. So I am going to discuss that continuous images of closed interval 0 1, and they will be of course paths, so form a special case of homotopy of maps. So we are going to get homotopy of paths in topological space, so that I can going to discuss graphically a path arc, a path arc equivalent to x is continuous map y such that I tends to x. So friends, this is the line, straight line, and this is 0 and 1, and the point is t, and it is the path. This is the set x, and the path is, this is the path gamma 1 and gamma 0. This point is called terminal point, and this point is called initial point. This point is called initial point. The map gamma and the point t, this point t is gamma t. This point is in here gamma t. The map gamma traces the image, gives you the curve. I talk of geometrically this curve. Homotopy between these two paths gamma 1 and gamma 2 are fixed at end point. So that f0 comma t equals to gamma 20 equals to gamma 10, and f1 comma t equals to gamma 11 and gamma 21. If such that I cross I tends to x, f0 is equal to gamma 1 and f1 equals to gamma 2. So if 0 comma t equals to gamma 1 comma 0 equals to gamma 2 comma 0 equals to x0, and if 1 comma t equals to gamma 1 1 equals to gamma 2 1 equals to point x1. Now you can see so friends, this is a graph. You see this point is gamma 2 and this point is gamma 1, and this is the t time, and this is 0 and this is 1. So this way it is ft, and this point equals to f1, and this is f0 equals to gamma 1, 0 comma 1 and 1 comma 1. So friends, this is a curve, and this is this way, this is gamma 1 and this is gamma 2, and this segment is ft or gamma t, and this is the point x0 and x1, and this point is gamma 2 is equal to f1 and gamma 1 equals to f1. So this is the path. A continuous family of maps parameter is by the time without the star the image would like this way. This is gamma 1, this is gamma 2. All of this collapse to a point, all of that collapses to a point, and you get a diagram. Homotopic is loops, a path starting from a given point and coming back to the same point. So homotopic is loops a path starting from a given point and coming back to the same point and coming back to the same point. Now friends, I want to discuss this portion, contractible stable portion. I have to discuss because I have already discussed this position. I have already discussed what is a f is called path homotopy between f and f dash. I explain with a diagram. Okay friends, with a diagram. Now I will discuss this portion with a diagram, contractible to simply connected. This portion I will discuss. This is the definition. Now I discuss this. Now I just try to explain this. Okay. Now this portion is called concatenation part. If alpha is path in X and beta is path in X are paths such that alpha 1 equals to beta 0, alpha 1 equals to beta 0. The situation as follows. This diagram is called X, and x0 is the x0 to x1, and x1 to x2. x0 is the terminal point of alpha, and x1 is terminal point of beta. x1 is ending point of alpha and x2 is ending point of beta. alpha is going unit time, and alpha beta such that I tends to x, b going from x0 to b going from x0 to x1 at double the speed in the half time in alpha, then from x1 to x2, then from x1 and x2 via beta, again in half the time. Alpha beta such that I tends to x, so t is equal to t tends to alpha 2t, where 0 less than equals to t less than equals to half, and t is sending to beta 2t minus 1, where half less than equals to t less than equals to 1. So continue, all the path is continuous. This path are continuous, and you compose two paths. So alpha is homotopic alpha 1, and beta is homotopic beta 1. Then alpha beta is homotopic alpha 1 and beta 1. So friends, I hope I can clear this concept, friends. Here is s in terms of t. Okay, so I already told that if f is path in x0 to x1, and g is path x1 to x2, then composition the composition f star g and fg, g is a path h given by hs is f2s, s belongs to 0 comma half, and f belongs to g2s minus 1, s is equal to half comma 1. So friends, this composition I have taught and I also explained in here. You will see that I explained the composition. Okay, and you will see this is our this is the alpha and beta in here, f and g. Alpha stands for f and beta g. So I hope that you can easily understand these definitions, alpha beta, with a diagram. Now friends, concatenations of paths. This is the concatenation of paths. Concatenation of paths respects homotopy classes. Path starting and ending a fixed point. So this is the pi 1 x comma x is equal to homotopy equivalence valence classes of paths from an ending at x. Homotopy respects the concatenation of paths. So friends, where is the composition? I have already discussed. This is the concatenation path. This portion is also called concatenation path. Homotopy respects to concatenations of paths. The multiplication gives binary operation. Said that the makes setting to a group that is called fundamental group of X. Fundamental group of X base at the point small x, and we get a binary operation, and homotopy classes alpha, homotopy class beta tends to homotopy class alpha beta. This is the concatenation. This is called concatenation. Concatenation. Operation is associative. There is an identity element, is just the constant path. I am looking at the path starting at x and ending with x and ending with x. That is a deep degenerate path. You map the whole interval to the point x. That a path by definition, because it's a constant map, is always continuous, so that's by definition of path it's called the constant path at x, and that path simply doesn't do anything, it just stands there. It stays put. Concatenate with any path, you are going to get back the path you concatenate it with. It's going to act as an identity element, and therefore identity element and then associatively is something. Inverse path is traverse in reverse directions. Reverse directions. The story is that provides replacing t by 1 minus t. T tends to 1 minus t. Reverse path, and automatically provides you with a path which is inverse to given path between, because if you concatenate it, you can see that it's going to be a trivial path, it's going to be a homotopic. Take a loop, then its inverse will be going the other way, and then thus I am saying this followed by this can be deformed to the constant path in the way, pulling this loop out at time t, so that just come back to 0. So there is a inverse element. Suppose the moving is this way and it will come in x. This is my path. So inverse path is this way. This is my inverse path. Inverse path is this way. This is inverse path. So whatever we have learned another is pi 1 x comma x is fundamental group. Fundamental group, and if x arc-wise connected, if x is arc-wise connected, that then pi 1 x comma x is isomorphic to pi 1 capital X comma x prime. So for any 2 points, so let's draw a diagram. This is a diagram, and this is the point X, and this is the moving this way. This is the path. Another path is X prime, and path is gamma, and this path is alpha. So for any 2 points X and X prime in X, putting this arc-wise connectedness, you can show that the fundamental group is the same of the isomorphism and this. So homotopy class alpha is sending to gamma inverse alpha gamma homotopic, and pi 1 x comma x into gamma sending to gamma star gamma hash is pi 1 x comma x prime, pi 1 x prime, arc-wise connected. Any 2 points can be joined by the arc gamma. That's a definition of arc-wise connectedness. First, you first go gamma inverse, which is just reverse of the path gamma, and you go by x, and then you follow by gamma, and this is principle gives you a loop base at x prime. I go from the point to a certain by a path and come back by the same path. That is also called, that also qualifies to be called a loop, because only condition is that starting point should be the same. Starting point should be the same. This is called loop. An ending point. That is the reason, because I have a path like a loop. Gamma inverse, then apply gamma inverse followed by alpha followed by gamma and equivalence class. I am not thinking gamma as a map. Never think that this gamma is not map. It is not mapping. So it is not confused that a lot of students, the gamma is map. In here, gamma is not map. Gamma is a path. This should not be configured with composition of maps. I mean, first go by gamma inverse, and then gamma go by alpha, then go by gamma. This is isomorphism groups. The constant path will go to the constant path. Constant path will go to the constant path. In fact, it take the constant. You will see that a space is contractible if a identity map is homotopic is a constant map. So whatever I say that constant path. What is the constant path? Constant path is isomorphism groups of constant path will go to the constant path. It will go to gamma inverse gamma and gamma inverse gamma, and is again homotopic. Why the fundamental group so important? It helps to distinguish between topological spaces, and that because it what is called a topological invariant. This is the main basic. What is the topological invariant? Pi 1 x is called topological invariant. If you change topological space by a homeomorphism, then the fundamental group first fundamental group will change only up to isomorphism. If two topological spaces are homeomorphic, the fundamental groups have to be isomorphic. Two topological space is are homeomorphic if two topological space are homeomorphic, the fundamental groups have to be isomorphic. The fundamental group have to be isomorphic. I want to decide that two topological spaces are not homeomorphic. The torus is not homeomorphic to the sphere. Torus is not homeomorphic to the sphere. The fundamental group is non-trivial is the same are trying to find loops that cannot be continuously shrunk to a point. The fundamental group of the sphere is trivial group. Sphere is trivial group. Is trivial group, and the sphere and torus are not homeomorphism. The fundamental group is non-trivial is the same as trying to find loops that cannot be continuously shrunk to a point. Two sphere and torus are not homeomorphism. The advantage of having the fundamental group, thus the theory of covering spaces, key ingredient. This is the key ingredient in the theory of covering spaces. So friends, fundamental group of any simply connected space, any simple connected space is isomorphic to 0, and every loop continuously shrunk to a point, and I can shrink a loop continuously to a point. It means I can deform that a loop to the constant map at that point, which is the identity element. So you are saying that every element is the equivalence class of every element is the same as the equivalence class of the identity element. That was if you take equivalence classes. So the group reduced to 0. So friends, fundamental group any simple connected, if I will take, I can write this is the 1 instead of this. So I should write 1 fundamental groups can be highly non-abelian. This is proof that it is highly non-abelian. Highly non-abelian. First fundamental group first fundamental group of sphere, I can write this way. First fundamental group of sphere equals to 0, and second and first fundamental group of complex place equals to 0. Can be contracted to a point. Any contractible space is a space that can be continuously contracted to a point. It won't happen to annulus or a cylinder. So fundamental group of annulus or punctured plane, annulus or hyphened punctured plane is isomorphic to Z. Pi 1 is the sphere is isomorphic to Z, and fundamental group of cylinder is isomorphic to Z. If you take a torus, so fundamental group of torus isomorphic to Z cross Z, that is isomorphic to Z composed Z, and this is the path, and this is also path 0 to 1. This is torus and this is also path 0 to 1, and homotopy classes of beta is sending to 0, 1, and homotopy classes alpha is sending to 1, 0, and pi fundamental group of torus isomorphic to Z cross Z mapped by sending alpha to 0, 1. So friends, now I want to close my lectures, and this is the algebraic topology. You can get a lot of books in the market, and this is very introductory video. I hope I can clear this total concept. You can get a lot of books in the market and algebraic topology. So thanks for watching.